In this video, I will present Bravais lattices in trigonal system. This is a slightly confusing topic. So, I am specifically discussing this particular crystal system because it requires some attention. So, there are two Bravais lattices in the crystal system, trigonal crystal system, HP and HR. So, you can see, and the symbol H stands for hexagonal. So, this itself is somewhat confusing, that the crystal system is trigonal, but there are two Bravais lattices which belong to that system and both are designated with the symbol hexagonal. P of course stands for primitive and R for rhombohedral. Now, crystal system, as you know, implies a certain characteristic point symmetry. This I keep emphasizing, and this is important to keep in mind, that a crystal system is not defined by certain relations between lattice parameter, but by a crystal having certain characteristic point symmetry. And if you think in terms of the 32 point groups, some of those point groups will have this characteristic point group symmetry. So, crystal system can also be thought of as classification of point groups having that characteristic symmetry. So, let us apply this to the example of trigonal system. So, if the crystal system is trigonal, then the characteristic point symmetry is one threefold axis, or in symbol just a 3. So, the point groups which will have this threefold axis out of the 32 point groups having a single threefold axis are 5 different point groups which belong to the crystal system, the trigonal crystal system. So, these are 3 bar, 3 2, 3 m and 3 bar m. That is in the Hermann Mauguin notation. In the Schoenflies notation, we write them as C3, C3I, because 3 bar is a threefold with a center of inversion. So, that is what is recorded or noted in the Schoenflies notation, that is a threefold as well as an inversion center. 3 2 is called the dihedral group, D3. 3m is a threefold with vertical mirrors, that is mirrors passing through the threefold axis, and 3 bar m is D3d, that is a dihedral group of order 3 with diagonal mirrors. So, D3d. Anyway, so these 5, so any crystal having these 5 point group symmetry will be by definition a trigonal crystal. But to denote these trigonal crystal or to represent these trigonal crystal, we need Bravais lattices, and as I pointed out that the Bravais lattices in the trigonal system, there are 2 of them. You have either the hexagonal primitive or hexagonal rhombohedral, HP or HR. P of course is a primitive, it is referred as a conventional unit cell chosen for this lattice, will be a primitive unit cell. In the rhombohedral, the conventional unit cell allowed are actually again 2. So, these 2 are known in the international table, and of course, one confusion also comes because different authors and different books sometimes use these terms in different sense. What I am trying to do is to stick to what the current international tables published by International Union of Crystallography is referring to. So, in this notation, the in the if you look at the international tables, the hexagonal rhombohedral space groups, HR space groups, are always referred to in two different unit cells or two different axial systems. One is the rhombohedral. These are called settings, rhombohedral setting. I will call it a rhombohedral unit cell, or hexagonal setting, which uses the hexagonal unit cell. And in this case, the rhombohedral setting or rhombohedral unit cell is a primitive unit cell, and the hexagonal unit cell is non-primitive. It is an R-centered cell, which is available only in the trigonal system. So, you can see that in the current nomenclature, none of the lattice or unit cell in the trigonal system has the name trigonal. They have name either hexagonal or rhombohedral. So, let us look at this in little bit more detail now. So, let us say hexagonal primitive unit cell or hexagonal primitive lattice. So, hexagonal P, you know, the conventional unit cell used will be a rhombus based prism. So, you have a rhombus A equal to B, the angle between them is 120 degree, and you have the height of the prism C, which is not equal to A. So, this gives you a hexagonal P unit cell of the hexagonal P lattice. So, lattice points, since it is primitive, lattice points will only be at the corners. You can see it in projection also. So, you have the rhombus. You divide the rhombus into triangle for just for reference. And there are lattice points here, which are representing lattice point at the base as well as lattice point on the top, 4 of them, because they will project exactly at the same location in the projection. This is called projection on basal plane. Now, the question is, we are talking of, just now we said that we are talking of trigonal system, which is supposed to have a threefold axis, one of the 5-point groups which have threefold axis. So, then, but this system, the hexagonal P lattice on its own will have a 6-fold axis. So, if I extend the, you can see the 6-fold axis better. If I draw the projection of few more unit cells, they will have lattice points here. So, if you look at any given lattice point, then let me focus on this one. So, you can see that that is surrounded by 6 lattice points here. So, the lattice itself will have a 6-fold symmetry. Then how is it? So, if it has a 6-fold symmetry, let me draw a hexagon here to represent the 6-fold symmetry. So, you have six-fold symmetry axis passing through each lattice point. So, then it is obvious that this can belong to a hexagonal crystal system, but how does it belong to trigonal crystal system? It will belong to trigonal crystal system only if we decide to put a motif having symmetry of the trigonal system, motif having one of these 5 point groups. All of them have a single three-fold axis. So, if I choose any of those point groups and place it, so let me make another drawing. So, let us look at now. I have drawn projection of many hexagonal P unit cell, and these are the lattice points. The base of the unit cell of course is rhombus, but I have divided each rhombus into equilateral triangles just for visualization. And if instead of what I told, that you have a six-fold axis passing through each lattice point, which is what is also happening here now, but instead if I decide to place a three-fold motif, one of those 5 point groups having a three-fold axis, and if I align the three-fold axis parallel to the C axis. So, in this projection diagram, let me just try to place a triangle. If I place a triangle, then the six-fold is disturbed and all the six-fold is converted into a three-fold. So, if you start with a hexagonal lattice, but use a trigonal motif consistent with the trigonal symmetry, you will get a crystal which is trigonal, but you will still use, for your reference, you will use a unit cell which is hexagonal. So, that is what is meant by a hexagonal P unit cell for a trigonal lattice. This triangle, I have used this as a triangle, but it can be motif with any of those 5 point groups. But finally, since that their threefold is along the C axis, these axes will get converted into threefold. So, it's an HP lattice of, we can call it an HP lattice of trigonal crystal system. So, that is this branch, Now, let us look at the other branch, the other lattice which is possible in the trigonal system, and that is hexagonal rhombohedral. Hexagonal rhombohedral, again we start, our starting point is again the hexagonal primitive lattice. So, let me outline the rhombus. So, this will be the rhombus unit cell. However, the lattice point now, instead of the corners will be lattice point, but we have two more additional points which correspond to the centroids of these two triangles, but their C height, the Z height is 1/3 here and 2/3 there. So, this is your new unit cell, and this 1/3 and 2/3 points are also lattice points. So, there are effectively now, so this is your HR lattice with HR unit cell. So, this is the hexagonal setting known as hexagonal setting. Hmm? Hexagonal setting, just to confuse you. Okay. So, this is an HR lattice, hexagonal rhombohedral lattice. So, lattice is rhombohedral, but the setting is still is hexagonal. We will see what is the rhombohedral setting soon. And here also you can have, in this hexagonal setting, you have what is called the obverse and reverse settings. So, what is shown here is obverse setting, but if you choose, let me mark this 1/3 point in another unit cell. So, that will be 1/3, this will be 2/3. Suppose we choose our axis. So, let us write down the coordinates, the full coordinates of these 1/3 and 2/3 points. So, the 1/3 point, if you look at the coordinate along x and y axes, so this is 2/3 in the x axis, 1/3 on the y axis, and 1/3 on the z axis. And this point is 1/3 along the x axis, 2/3 along y, and 2/3 along z. So, this black unit cell is what is called the obverse setting. Lot of jargon, lot of terminology to confuse you. But obverse setting. But we could choose our x and y axis differently, rotated by 60 degrees, so to say. So, let me highlight this red unit cell. Say x prime and y prime. So, now the red one is reverse setting, where if you now look at the coordinates. So, this coordinate now, the one which I am outlining in red at the moment, becomes, if you look with respect to the x prime y prime axis, the first one is 2/3 x coordinate. This red point, the current red point, is 2/3, 1/3, and then the height is 2/3, and the other point, if you look at, its coordinate is 1/3, 2/3, and 1/3. So, you can see that these coordinates, the red coordinates or coordinates of internal points with respect to the red axis, and coordinates of the internal point with respect to the black axis are slightly different, the way 2/3 and 1/3 are distributed along x, y, and z. So, these two settings are known as obverse and reverse setting for the hexagonal setting for hexagonal R lattice. Now, let us come to the rhombohedral unit cell choice for hexagonal setting. So, I again start with the lattice points. These lattice points are at 0, 1, and all other integral values, all will project at the corners of this hexagonal or triangular network, as you may please to call it, and these points are now 1/3, 2/3. Let me mark some more points. Now, suppose I start at the 0 level with that lattice point and join 3 of these lattice points which are at 1/3 level above this point, and call these as my basis vectors. You can see that these 3 vectors will have equal lengths because all of them are equally distributed, symmetrically distributed about the central point. So, and means if you so wish, you can use trigonometry and geometry to show that these vectors are of the same length. So, we have a unit cell in which A equal B equal C, and you can also see that these angles, now they are no more 120 degree because of the z coordinate which is 1/3. So, they will be 120 degree only in projection if 1/3 was actually 0, but now since these points are above these centroids. So, these 3 angles between A and B, you call that gamma, B and C alpha, and A and C beta. So, these 3 angles are also equal, but they will not be 120 degree, they will be less than 120 degree. And any 3 vectors define a parallelepiped. So, they will define a parallelepiped which will be a rhombohedron. So, parallelepiped defined by these lattice parameters or the 3 vectors is a rhombohedron, and this is then called the rhombohedral setting or rhombohedral axes. And this is quite often in many textbooks you will find this unit cell as the definition of the trigonal lattice, but you can see that the trigonal lattice, this is only one of the possible choices for one of the possible types of lattices. So, 2 lattices, hexagonal P lattice and hexagonal R lattice. In hexagonal R lattice, you have centered cell with the 2 lattice points inside and 1 lattice point at the corners, and in the hexagonal R lattice there is another choice of unit cell which is the rhombohedral axis or rhombohedral choice. So, you can, if you so wish, you can show this in 3 dimensions, but I do not want to venture into that. I leave it to your imagination that what you will be getting here. So, if these 2 vectors, for example, if you join, you will reach the next level 2/3. So, that also will be a vertex of your parallelepiped, and then finally on the 2/3 if you join, add the vector C, you will head towards the center again, but since you are starting with 2/3 and C vector further raises you by 1/3, you will come to a height 1 above the original center or original origin. So, that will, if you do this, you will get a rhombohedron or a parallelepiped with 2 vertex along the C axis 0 and 1, and then 3 vertices at 1/3, 1/3, 1/3, and 3 vertices at 2/3 height. So, that gives you the 8 vertices of the rhombohedron. So, I hope I have made an attempt to clarify the situation a bit, but if I have confused you even more, I am sorry about that. Thank you very much. Bye bye.